Hello, welcome back. Today I have something really special for you. We're going to figure out what happens if we put 24 eggs in a vacuum chamber and pull a vacuum on it. Will the eggs explode and go everywhere, or will nothing happen at all? And along the way, I can almost guarantee you that in this video here, you're going to see more about eggs and dive deeper into eggs than you ever thought possible in a video. We're going to do some crazy things. I'm going to squeeze eggs in my hand and see if we can get them to explode and check that out in slow motion. We're actually going to put some balloons and other bags in a vacuum chamber before we do anything with the eggs and take a look at those in slow motion as well. I've even cut an egg in half to see if we can go inside of an egg and look at what it would sort of feel like to live inside of an egg from the vantage point of a yolk inside of an egg. So stick with me, we're going to do some amazing, cool things with eggs today. Now, before we do anything with eggs, let's take a look at what happens to a bag filled with air and we put it inside of a vacuum chamber. You know, there might be a little bit of air inside of an egg, but not very much. It's mostly a liquid in there. So before we deal with that, let's see what happens to an air-filled sack. And so for this, I have this little packing material here, which is kind of convenient and nice. So I'm going to put that in the bottom of the vacuum chamber. Start to think for yourself, what do you think will happen to this? Well, you know, we have atmospheric air pressure all around us and pushing on everything, and there's air inside of that bag. So as we pull a vacuum and pull the air away from the outside, let's see what will happen. Bags in a vacuum chamber, 3, 2, 1, here we go. All right, we're already at 3/4 of an atmosphere. You can see the bag swelling, approaching half of an atmosphere. Not quite there yet. And we're right now at half of an atmosphere. Let's see if we can get these bags to pop. And they're getting very close to the top here. Let's see if they pop before it reaches the very top where the air is being sucked out. Ooh, it's getting very, very big at the bottom. That looks really cool. It's about to blow right there at the bottom. There's one that goes, two that goes. Let's see how far we can go. We're at 1/4 of an atmosphere. And the last one's about to go. Let's see if it can go before it chokes off. And there's the last one down there. Wow, it looks like a bubble down there. That looks really cool. And there it goes. Let me turn it off. And it's always fun to see what happens when we put the air back in the chamber rapidly. Everything's flying around, of course, because air is rushing back into the chamber. All right, so what happened there, and why do we even care about that? I want you to see what happens to an air-filled sack in a vacuum, because we're obviously going to do that with eggs, and we want to see if the same thing happens or not. And so when we have pressure or any air inside of a closed container, there's some sort of pressure because of the atoms moving around inside of the bag. And there's atmospheric air pressure pushing on the outside. If we remove the outside air pressure, then we're removing some of the force pushing on the outside, and so from the inside, that's why it begins to swell, because the pressure then begins to push from the inside, eventually rupturing the bag there. All right, next thing we're going to do is put a balloon in this vacuum chamber. I think you can probably guess what probably will happen. Let's see if we can get this thing to get large and pop. Just going to fill it about that much, not too much here. Let's just tie it here. Drop it in. And let's pull a vacuum on a balloon and see if it will actually pop or not. I don't know if it will. We'll seal off the vacuum here. Balloon in vacuum chamber, 3, 2, 1, here we go. All right, so we're at 3/4 of an atmosphere, almost to 1/2. Now we're at 1/2 of an atmosphere. We're lower than 1/2 of an atmosphere now. Approaching 1/4 of an atmosphere, so this balloon's obviously getting bigger. Normally you blow balloons up and they get big. Here we're not adding any more air, we're just removing pressure from the outside, which forces the balloon to get larger from the inside out, from the internal air pressure pushing. We're at 1/4 of an atmosphere. Notice right now what's happening is the balloon is now covered up the inlet of the pump there, so I can no longer suck any more air out. So for this situation, I can't pull any more air out because it's covered up where the air is sucking from. So we obviously did not get it to pop there. Let me close that off, let the air back in. All right, so obviously I couldn't get it to pop there, but I think just based on the strength of this balloon here, that even if we didn't cover up that hole that was sucking the air out and stop the process, I don't think we could actually pop this in this vacuum chamber. I think this balloon would stretch to fill almost the entire volume there. As we suck the air out, I think it would just stretch and eventually it wouldn't pop. So what I did is I took a needle and I affixed a needle to the underside here, right near where the inlet is. I put it all back together, and then I did it in slow motion. So I want you to take a look at that now and see what happens to a balloon when it's punctured inside of a vacuum chamber. Now, one thing I want to talk about before I move on is that this rubber is very stretchy. It's very strong and it's very stretchy. We call that elastic. This plastic here is very strong, very, very stretchy. If you try to pull on this, you know, I can pull with quite a bit of force and be unable to actually break it. But we all have that experience of once you get it started, then it's very easy to rip. So for instance, in between these layers here, there's a perforated, kind of like it's kind of microscopically cut between here. But if I pull apart, I can pull pretty hard and not rip it. But if I go to the end and I just get it started just right there, just get it started a little bit and then begin to pull, then it's much, much, much easier. You see how fast it rips apart when a tiny microscopic tear is there. And I could do the same thing anywhere. I could get it started right there, and then once it's started, it's very, very, very easy to rip. We all know that. Why is that? Why do some things, like a pencil, if you get a pencil, you can feel it elastically bending, but eventually it snaps, right? It's not really elastic beyond a very small bit there, but things like rubber can stretch very, very much more. Why is that? Well, that's because rubber, like in this balloon, plastic like here, this is called polymers. A polymer in chemistry and physics is basically a very long chain molecule of any kind really, but in this case it's a very long chain molecule consisting of carbons, hydrogens, and sometimes even oxygens that are just, it's like Legos, one after another connected to another, very, very, very long molecules. And so because of that, on a microscopic level, when I pull on it, these very long microscopic polymers are attracted to each other, just like most molecules are attracted to each other in some way, otherwise everything would fall apart, right? And they can slide past each other to a great degree. And these polymers can be folded and they can be curled up and then they can be uncurled into a long line. And so that's what gives it its elastic nature. But in something like wood, when we bend a pencil back and forth, right, we feel that springy nature because there's some molecular attraction between the molecules there, but they're not very long chain polymers. So eventually when you go past its point of no return, its breaking point, then the bonds are actually broken and then the thing snaps in half. So things like glass will shatter, things like pencils can snap, but long polymers like this are very, very strong but also very, very elastic. All right, before we actually put the eggs in the vacuum chamber, let's talk a little bit about this thing called an eggshell. We see it all the time, but it's really fascinating. So an eggshell is a very hard structure that protects a very delicate interior, and it serves a very special purpose. It obviously needs to be strong because birds, will sit on their eggs, and so it has to be strong enough to withstand that. But also, it acts as a semi-permeable membrane that allows gas to go in and out, like oxygen to go in, and carbon dioxide to come out while keeping the liquid held on the inside, the yolk and the white that's on the inside. So it allows gases to transfer back and forth, a basic form of respiration before the chicken is fully developed or before the bird is fully developed. It's allowing CO2 and oxygen to pass back and forth through microscopic holes in the egg there. And the egg is obviously very strong. It's made mostly of something called calcium carbonate. So some calcium atoms, you think about calcium making your bones strong, right? Carbon, oxygen, so calcium carbonate, right? Now it's very, very strong. If you have your hand here, now if you're a really strong person or really practice, or if you cheat a little bit, you can get this to happen. But if you take an egg in your hand like this, and don't put a pressure point with your finger, but just wrap around it and squeeze. Most people cannot break an egg. If you do it, be careful, do it outside, do it over a trash can so it can make a mess. If you put a pressure point, if you put your thumb here and push with your thumb, you can overcome the strength and break it. But I'm squeezing pretty strong, maybe not all of my strength, but a good chunk of it, and I can't break it. And the reason is because the shape of the egg is this weird ellipsoid, not symmetrical, but it's an ellipsoid. And so as I squeeze, then every part of the shell, or most of it, is under compression. And this eggshell, when it's being compressed along the direction of the shell, is very, very strong. But if you put your if you bang it against something hard like this, then or if you push with your thumb with a very high pressure here, then you're pushing in and you're deforming it inward, and you're almost, instead of compression, you're putting it in tension. You're pulling it apart. That's what tension is. And these things are not very strong in tension. They're very strong in compression though. So if you put your hand around evenly and squeeze, then you usually can't get it to break. But if you put your thumb and squeeze really hard, you know you can. The other thing you can do, here I have a dime here. And so if I just put this in my hand, see, I can't really break it too easily here, but if I put this here and then do it like this, and I'm putting a pressure point, I'm essentially concentrating a lot of the force on the edges of this dime here, and then when I do that, very, very easily, I broke this egg here. Give it a try, but be careful, it's really messy. So what I want to do is put them in the vacuum chamber. I suspect nothing will happen, but maybe I'm wrong and maybe we'll get some action, we'll see. What I'm going to do is take half of the eggs, I've got 25 or 26 eggs I think, and what we're going to do is I'm going to poke holes with this needle here. I'm going to poke a hole in the top of about half of the eggs. And then that way, maybe we'll get a geyser or something, maybe not. But I want you to make your own prediction, and we'll talk about the difference between how eggs behave and bags and balloons behave after we're done. So let's go ahead and come over here and begin to put some holes in some of these eggs. I'll just kind of go here and just kind of poke a little hole there. There's one right there. Even with a needle, to be honest with you, it's kind of cool. Even with a needle, it takes a while, especially these big brown ones. Now, you can get in there, but it's difficult to do, and you have to work at it. So I'm going to do this for half of them, and then we're going to load them up, put them in the vacuum chamber. I thought it would be fun to try to actually cut through the end of an egg with a hacksaw and try to see if we can go inside of the egg with the camera. Now, the first time I actually did this, I made a huge mess and applied too much pressure, and the egg actually shattered. Now, I learned 2 lessons from this exercise. First, try to wear gloves in case you get your hands messy again. Second, apply a lighter pressure with longer strokes. And when I was able to do that, I was able to actually cut through the eggshell over a period of about 5 or 10 minutes and make a nice hole in the end. Notice as the saw goes back and forth, you can see the particles of calcium carbonate kind of flaking off and flying off of the saw blade. After this first test, I was able to go all around the circumference, doing this over and over again, and actually slice the end off of the eggshell. Now here's the end result. I have absolutely no reason to do this other than I just wanted to see if I could do it. Here's the eggshell with the end sliced off, and we send my probe lens all the way through inside of the egg, sort of from the perspective of if you were living inside of this egg. If you look carefully when you get to the very back of the egg, you can kind of see these markings and sort of tendrils, almost like blood vessels of some sort of form inside of the eggshell looking from the inside. I don't know exactly what purpose these serves, but obviously it's to support the embryo during development. Now I have more of the eggs on the top that have the holes, and that way if we get any geysering or anything like that, hopefully we'll see it coming right out of the top there. It looks like I have just the right amount of eggs, actually. I have one more, and we'll just put that one down here. Hopefully nothing catastrophic happens because I can't really fit it anywhere else. So we'll just put it right over there. Oh, I have 2 more actually. We'll put that one right over there as well. Let's see what happens. 3, 2, 1, here we go. All right. So we're at 3/4 of an atmosphere, approaching 1/2 of an atmosphere. There's 1/2. All right, then we will approach our way to 1/4 of an atmosphere. Look, it's already coming out of that one over there. That's really cool. Check that out. Okay, there is 1/4 of an atmosphere right there. Already making a mess. We're going to let it go as far as we can. Let's see what happens. But nothing major, nothing like an exploding set of eggs or anything, even though that was pretty cool over at the end. Nothing happened. Why? Or I shouldn't say nothing, amazing happened. Why is that? Well, because these eggs are filled with a liquid, right? Not a gas. Or if there is a gas in there, it's a very small amount of gas. And we already saw how strong this eggshell is. So that whatever tiny amount of gas was in there was not enough to push on the outside and rupture the egg, except in that one case, which is kind of interesting. All right. Even when we had the holes punched in the eggs, all these eggs on the top have holes, we didn't really get any geysering. We saw a little bit of leakage over here, which is now gone when we put the air back in. Why is that? Well, a gas tries to fill its container in all directions. The pressure of a gas, we say, exerts against the walls of the container because it's constantly colliding. Like the gas inside of this chamber is constantly colliding with all surfaces, so it's going up, down, sideways, colliding in all directions. That's what we call the internal pressure. So if we remove the outside pressure, then that internal pressure then begins to expand it in all directions, like with the balloons and popping the bags. But in an egg, it's a liquid. Now, we also talk about liquids having pressure too, and they do have pressure. Like going under a swimming pool of water, there's pressure on your ears. That's pressure due to the weight of the water or the liquid as we go down in depth. And so we remove the outside air pressure, and there is not enough of a force pushing from the inside out to do anything dramatic. So a liquid has its own unique behaviors in a vacuum, but exploding eggs, unfortunately, isn't one of them. So what I'd like to do now, just since we have all these eggs, let's go ahead and crack all the eggs in a container, whisk them together, and let's put the eggs in here, and let's just see if it's possible to get these eggs to boil in a vacuum without adding any heat. And let's see if the eggs cook along the way anyway, because as you know, the boiling point of a liquid depends on the pressure. If we remove the pressure, then we might be able to get the eggs to boil. I'm not sure. We're going to check it out and find out. I started shooting these high-speed shots of eggs cracking and dropping into the bowl, and when I started looking at the footage, it just absolutely mesmerized me. So I'm going to go ahead and leave them in here. Basically, these shots range from about 1,400 frames per second all the way up to maybe 4,000 frames a second, depending on the shot. And it's almost like these eggs, when they're falling, it's like they're in a different universe of their own. We see this stuff with our eyes, but when you slow it down, you can just see every little drop, the surface tension, the viscosity. You see details that we just can't see with our senses. And so it's fascinating to me. So I hope you enjoy these. Now, for the photography nerds out there, when you shoot really high-speed footage like this, it's a specialized camera, and the frame rates are so high that you need a ton of light. My normal studio lights is not even close to what you need for this. To get these shots, I have to have three 300-watt LED spotlights, essentially. So about 900 watts just in lights, and these lights are not omnidirectional. They're spotlights that go directly on. So it literally would blind you if you looked at these lights with your naked eye. But the shots I think that we get as a final result are amazing. So I got some new lenses. One of these lenses is the probe lens. It's the same lens that lets us go inside of the balloon and inside of the egg. And I just couldn't help but use it here to make some really cool shots of whisking eggs. Of course, we have the slow motion shots as well, and I just couldn't resist shooting those because anytime you see this highly viscous liquid like an egg yolk whisked around, it just looks really fascinating in slow motion. All right, this is going to either make a huge mess or do absolutely nothing at all. Let's take a look. Eggs, trying to scramble them in a vacuum chamber. Will they boil or not? 3, 2, 1, here's the vacuum. All right, we're at 3/4 of an atmosphere. And now we are at 1/2 of an atmosphere. Okay, passing half an atmosphere. I see some movement in there. Maybe that was just my imagination. I thought I saw some movement at the bottom there. Okay, now we're approaching 1/4 of an atmosphere. I see some bubbles coming up. I do, absolutely. It's not my imagination. So we see some bubbles forming. Let's see, by removing the outside air pressure, how messy this gets. I have no idea. Okay, we're past 1/4 of an atmosphere. Got some big bubbles in the center. Ooh, looks like a lot of bubbles are forming. Okay, we're almost to the limit of what this vacuum pump can actually do. Let's just keep pumping. Oh, it looks like the eggs are swelling up. Oh my goodness. I think this might make a big mess. Oh, it's definitely swelling. So whatever dissolved gases were in there are coming out and making bubbles. And this is going to make a mess. Ooh. Okay. And right over the top. Yep. We're in a mess territory here. Wow, looks very foamy. Almost like a curtain. Wow, check that out. That is really neat looking. Oh my goodness. So why is it boiling? I mean, basically that's what's happening. Is it's kind of boiling and also dissolved gases are coming out. Why is that happening? Well, because liquids are easier to boil at a lower outside pressure because it's easier for the molecules to escape and to go off into the outside environment because there's less pressure from the outside. Wow, this thing is like baking a cake. Oh my goodness. You can see the structure of all the bubbles there. So we have some dissolved gases coming out. We have some water that's kind of boiling and making a bubbling kind of sensation here. We have like a caldera or some sort of valley in the center of this thing. I'm going to be scrubbing this thing for days. Okay. All right, and we're going to let the air back in. 3, 2, 1. What happens there? And it just collapses. And here is that footage sped up so you can see the whole process a little faster. Consistency is the same, more or less. Let's touch it. It's nice and cool. From another video I've done, I've already talked about that things get colder when they actually boil. We don't notice it on the stove because we're adding heat from the bottom to get it to boil. And so we kind of think of boiling as something we add heat to and it gets hotter. But the act of boiling itself, the hottest molecules, which are the most agitated, actually escape and they leave the surface. Like boiling water, the steam comes off, leaving behind the cooler bulk liquid behind. So a thermometer in boiling water in a vacuum actually goes down because everything left behind is cooler than the hot particles which have escaped. So the reason this thing boils and we've scrambled eggs, so to speak, in a vacuum is because the outside air pressure is lower. So it's easier for whatever water molecules are in here to escape because the outside air pressure is lower. And because of that, we get the boiling process. Of course, it makes all the foam because we have a lot of elasticity in the egg yolk. And so it kind of makes that foamy situation that we saw. I really hope you've enjoyed what we've done here today. I was curious, if we take a whole egg and put it in a vacuum chamber, what would happen? Would it explode or not? And what we figured out is that in general, it doesn't really explode, although we did see one of them kind of rupture a little. Maybe that was a little bit more weakened. But in general, eggshells are really, really strong, and they have to be because they support life in the most vulnerable state in the beginning there before it hatches from that egg. So it has to be durable, it has to be strong while allowing CO2 and oxygen to travel across the boundary there. But if we crack eggs and if we put them in there, then we can get that substance to quote unquote boil, even though it's not happening at a high enough temperature to what we call scramble an egg or boil an egg. It looks the same, but the boiling process is happening. So yes, we can scramble eggs in a vacuum chamber, but it doesn't really change the consistency of the egg at all. I hope you've enjoyed what we've done here today. Please drop me a line, let me know what you think, and don't forget, always stay curious. Learn anything at mathandscience.com.